Alright, hello everyone. How are you all doing? So, today the topic of discussion is going to be around interactive problems. I'll be discussing about what an interactive problem is and how to approach an interactive problem, that is, the general approach while tackling any interactive problem. And for the most part of the video, we'll be trying out a 2100 rated problem on Codeforces and I'll be discussing its solution. And towards the end, you'll realize that it is actually not that difficult at all and it is very much solvable even though it is highly rated. And so I hope that after watching this video you will feel more confident about actually attempting an interactive problem during a live contest, right? So yeah, let's begin. Let's get right into it. So what is an interactive problem? Let's see. So in general, on Codeforces or anywhere on any competitive programming website, while attempting any problem, you have been given with the size of an input, right? So you are given an input and there is a size of the input. For example, you have been given an array of size n, or maybe you can be given with a tree with n nodes or something like that, right? And basically what you have to do is you need to process that input and somehow come up with an algorithm which is efficient enough and which gives you the right answer of whatever has been asked in the problem, right? So in a normal problem, non-interactive, you need to optimize the time complexity or maybe even some space complexity requirements and come up with an optimal algorithm. But that's not the case in interactive problems, right? In interactive problems, what happens is there is an interactor and you actually talk to that interactor. And while talking, you ask something and the interactor gives you some information of about whatever you have asked. And this one exchange of information is called a query. So before getting into interactive problems, let's define what a query is. So a query is basically, it is an exchange of information between your code and the interactor, right? So basically the checker is an interactor and you ask something to the interactor and it gives you the results, and this exchange of information is called a query. And in interactive problems, rather than optimizing the time complexity, I mean, I'm not saying that you do not need to optimize the time complexity at all, but mostly rather than the time complexity, instead of the time complexity, you have to mainly optimize on the number of queries that you actually ask. Right. So if this seems to be a bit off to you and you are overwhelmed by this, let's look at an example, right? So I'll look at an example of an interactive problem. Let's say the problem is you have an array. So basically the interactor has an array, and in one query you can ask the element at any position, and the interactor will actually tell you what that element is. And you have been given the size of the array beforehand, and finally you need to tell the maximum element, right? Find the maximum element. So what you'll do is you will take n queries, and in each query you will ask the interactor what is the element at the ith position. For I going from 1 to n, you'll do that, and once you do that, you'll finally have the information about the entire array and you can easily find the maximum element. So yeah, that is what an interactive problem means. I hope I was able to explain the actual meaning and the definition of an interactive problem. And right, so let's move ahead and talk about how to approach an interactive problem. I've already told you guys that the main goal of us is to actually optimize on the number of queries we ask rather than the time complexity. So in the problems we have been given, we are always given a query limit. For example, something like this will be given. So take no more than x queries. So something like this will always be given in the problem, and let's see how to approach any interactive problem. So there is actually just one basic thumb rule. So you always try to find a relation between the query limit and the size of the data structure. So most of the times you are going to have an array or maybe a tree, something like that. For example, in the previous problem we had an array and we knew the size of the array beforehand, and we also knew the query limit beforehand, right? So what you have to do is you need to find a relation between the query limit and the size of the data structure, and once you do that, you actually have to come up with an algorithm according to the relation. So sometimes you'll realize that, for example, n can be up to 10 raised to the power 6, and the number of queries have to be less than equals to 1005. Something like that might be given to you in the problem. So in this case, the relation is somewhat like query limit is approximately equals to the square root of n, right? So that gives you an idea that the query limit is actually equal to the square root of n, somewhat equal to. So in one query, if you can find the value of square root n elements, then in square root n queries you can actually find the entire array, right? It is possible that in the problem you need to find all the elements of the array. So in one query, if you find out the value of square root n elements, then it is possible that in utilizing all the queries you can actually find out all the elements. So you try to come up with an algorithm which works like that, which works in a way that one query will give you the value of square root n elements, right? Sometimes, or maybe most of the times, more than half of the times, what will be given is q will be quite close to log of n, right? So in such problems, what you'll realize is that you have to do something related to binary search, right? Because we all know that the time complexity of binary search is log n, and when q is close to log n, we know that if we do some kind of binary search, then log n queries will be enough for us, right? So yeah, that is the general approach you always imply when you are trying to solve an interactive problem. Try to find a relation between the query size and the size of the input. And I'll take another example. Sometimes it's possible that q is equals to something like 5n by 2 or maybe 6n. So in this case, again, you can find the relation, and if q is equals to 5n by 2, you know that if using 5 queries you can find 2 of the elements, then you are done, right? So yeah, just look at the query limit and try to form an algorithm using that, and most of the times you will be able to do it. And interactive problems are generally highly rated because a lot of people tend to actually skip them. So yeah, so this is the general approach while tackling any interactive problem. So without any further ado, let's start solving the problem which we all are here for. And this is the problem guess the maximums from Codeforces round 646 division 2. It is a 2100 rated problem, and once I tell you guys the solution, you'll realize that it is actually not very difficult to think about. If you want to give it a try, you can just pause the video and try it on your own. And irrespective of the fact whether you want to try or not, you are advised to pause the video and actually read the problem. And alright, let's just get into the solution. So let's see what the problem says. So we have a password to a lock, and the lock has k slots, and each slot can hold an integer from 1 to n, alright. And the password is a sequence of k integers because there are k slots, and for each slot we have an integer. All the integers are in the range from 1 to n, and yeah, that's that. And also we have an array a of n integers, and what we are doing is we are dividing the array into k non-empty mutually disjoint subsets. So we are dividing the array into k subsets, and there is no element which is going in more than one subset. However, it is possible that an element does not go in any of the subsets, because the problem doesn't say that all the elements must go to any subset, right? Yeah, so we are dividing the array into k subsets, and basically for each subset, the ith subset, the answer for the ith subset is going to be the answer for the ith slot of the lock, right? So it is going to be the password for the ith slot of the lock, and let's see what the definition of an answer is, right? So they have given that pi is equals to maximum of j doesn't belongs to si a of j, which translates to the maximum element of the array after removing all the elements in my current subset. So for the ith subset, the answer to the ith subset is going to be the maximum of all the elements of the array after excluding all the elements of the ith subset. So we have the entire array. To find the answer for the ith subset, we just remove all the elements of the ith subset and find the maximum of the array, and that is going to be the answer to the ith slot. Great. So this is that, and we have also been given then that n is up to 1000 and k is up to n. Also, this is the line which I was talking about. You can ask no more than 12 queries. But before that, let's see what the definition of a query is here. So according to this problem, in a query, we can give any subset to the interactor, and the interactor will just tell us what is the maximum element in that particular subset. Great. So we are allowed to give any subset. There is no restriction on what subset we can give. We can give any subset which might not be any of these s1, s2 up till sk, right? So we just have to give a subset of the array, and the interactor is going to tell us the maximum element in that subset. And using such queries, we need to find out what the maximum element is. And we need to make at most 12 queries, and again we realize that if n is up to 1000, then log of n is up to 10, and this 12 is quite close to log of n. So this actually hints us that we have to use binary search, and that would be the case in most of the interactive problems, right? So let's get into the solution. All right. So let's say I have an array like this. And what I'm going to do is I'm going to shuffle the array so that an element in a subset come together. So let's say this is first subset, this is the second subset, and so on. Let's say this is the end of the kth subset, and these are all the elements which do not belong to any subset, right? So this is the first subset, this is the second subset, maybe this is the third subset, and so on. This is the end of the kth subset, and for all these elements I can say that these elements don't belong to any subset. Great. So this is done, right? So I have divided the array into k subsets, and obviously the subsets might not be contiguous, but I'm shuffling the array such that all the subsets come together, and nothing fancy I'm doing here. So once I have done this, let's consider two cases. As always, there will be two cases here. Let's see case 1. Right, so we have also been given that the elements need not be distinct here, as you can see. So let's talk about the maximum element, right? So the maximum element's frequency can be 1 or it can be greater than 1, but it doesn't actually matter. The first case is there exists no subset which contains an occurrence of the maximum. And case 2 is similarly going to be that at least one subset contains an occurrence of the maximum. Great. So before I go on and discuss about the two cases, the first thing I'm going to do before even considering at the cases is initially I'm going to ask a query on the entire range from 1 to n. So if I do that, I now actually have the maximum element with me. I now have the maximum element and 11 queries remain. Since log of 10 raised to 3 is 10, I still have one extra query, and I can also do a binary search. And if I do everything that I have mentioned, I would utilize exactly 12 queries. One query to find the maximum element, 10 queries for the binary search, and one query is still remaining. And let's see what I'll do with that. So this is case 1, right? So there exists no subset which contains an occurrence of the maximum element, and that just means that the maximum element occurs here. Let's say this is the index of the maximum element, right? So the maximum element is occurring somewhere here, if you guys can't see. So let me just remove it. Yeah, so this is where the maximum element is occurring. Let's say here. Right, and now if we look at the definition of the answer for an index for a slot, you'll realize that the answer is equals to the maximum element of the array after removing all the elements of the particular subset. And one thing we realize is that in this case, the answer for the first subset is going to be the maximum element, that for the second subset is going to be the maximum element, and we can use this argument for all the subsets because the maximum occurs in none of the subsets. So if I remove a particular subset, then the maximum would still not be removed, and I'm sure of that. So this case is really easy, and I can just say that the answer for all the subsets or slots is just going to be max, where max is the maximum element of the array. Great, so this is done. Now let's talk about the second case, which is more interesting. So there exists at least one subset that contains an occurrence of the maximum, and what we are going to do is we are going to find that subset. And of course I'm not denying the fact that there can be multiple subsets, but my goal is to find just one such subset. And let's see what happens when I have found just one subset like that. So let's assume that subset number 2 is the subset which contains the maximum element. So here is a maximum element. Now again, if we do that, we can easily observe that the answer for all the subsets other than the second subset is going to be max. Why? Because if I remove a particular subset which is not subset number 2, then the max is obviously not removed. So the answer for all the other subsets is just going to be max. So the observation here is let I be the subset containing the maximum, then the answer for all other subsets is just max. And also the answer for any subset can be just found with one query. So the answer for the ith subset can be found using a separate query, right? And how do I do that? I will query the entire array minus this subset, and I will just find the answer for this subset, right? Because the answer is going to be the maximum of all the elements after removing this subset. So I'll just take all the elements, remove this subset, and give it to my interactor, and the interactor will tell me the maximum element, which is indeed the answer. So this way I can calculate the answer for all the subsets. So I'm done, right? But actually there is one problem. I haven't actually discussed how do we find this subset which contains the maximum. And this is where the binary search comes at action, right? So let's see what I'm doing here. So I'll be using binary search to solve for this subset, and basically in binary search we take two indexes, right? We take an L and an R, which is our search range, and in every iteration of the binary search, if we are successfully able to reduce the search range by half, then it's good for us, then the binary search is going to surely work. So let's say I start with my L from here and my R from here, right? Okay, now I realize that the middle will be somewhere around here. So let's say this is the mid, okay, And now what I do is I query for the union of all the subsets from L to mid. I'm going to repeat that. I query the union of all the subsets from L to mid. That is all the elements in the first subset combined with all the elements in the third subset combined with all the elements in the third subset. And I know that all the subsets are disjoint, so combining them is not a problem for me. I can just take a vector and or add all the elements in these subsets to my vector, and I'll be done. So once I query that, there are again two cases. The first case is that the result of my query is actually equal to the max, and the second case is when the result of my query is not equal to the max. So when the result is equal to the max, which will be the case here since the max lies in the second subset, I can just say that my search range is actually reduced by half, and I can do r is equals to mid. And why is that so? That is because I know that there is a subset in the range from L to mid which contains a maximum, right? Because I have queried for the union, so there actually has to be a subset from L to mid which contains the maximum element. Great. And the second case is when the query result from L to mid is not equals to the maximum. In that case, again, I know that if there exists a subset which contains a maximum, then it has to be in the range from mid plus 1 to r, right? So again, I have successfully reduced my search space by half. So this means I can apply binary search. And let's write the binary search once for clarity. So binary search, so we have L and R, and again we do mid is equals to L plus R by 2, and what we do is we query for the union of L plus 1 up till mid, and if this query is equal to, so the first case is that this query is actually equals to max. In that case, what I can do is I can simply say my R is equals to mid, and if that's not the case, I can just say my L is equals to mid plus 1, right? So let's see what will happen after binary search gets terminated. So when we come out of the binary search, also we know that the binary search will take at most 10 queries because the ceiling function of logarithm of 10,000 is just 10, so it will take at max 10 queries. Now we know that when we come out of the binary search, then if there exists a subset containing the maximum, then it has to be the Lth or the Rth subset. It doesn't matter because L will be equal to R. So yeah, if there exists a subset which contains a maximum element, then it would be equal to the Lth or the Rth subset, and this just means that I have successfully found a subset which contains the maximum element. And of course, if there is no subset like that, then we are just in case 1, and the answers to all the slots are just going to be max. And if that's not the case, I can just query for the maximum element in my Lth subset, and the answer for all the other subsets is surely going to be the max. And what that means is we have successfully solved the problem, right? And I hope you realize that this problem was not actually that hard, and just because of the fact that it was an interactive problem, it was rated highly. And yeah, this is how we can solve it. So one query is going in asking what is the maximum element of the array. At max 10 queries are going in the binary search, and then finally we have one query remaining. So irrespective of the fact whether there is a subset which contains a maximum element or not, I will just query for the Lth subset, and the answer for all the other subsets is just going to be the max. Right, so this was the solution. Let's just look at the code once. So this is the code. Essentially, I am just making a separate query function because, yeah, so that is my advice to you guys. So while solving an interactive problem, always use a separate query function, because if you don't do that, your code is surely going to get a lot messy. So yeah, I have just made a query function which takes a vector, and the format for the query is given in the problem. You can check that out, and it just returns the response, and this is the function which prints the answer. So yeah, these are the two functions that I have made. Now let's come to the actual problem. So I take in the input of n and k, and then I'll be provided with all the k subsets, and I take that as my input as well. So yeah, and now I make a vector all which contains all the indices from 1 to n, and what I do is I calculate mx as mx is equals to query of all, and this gives the maximum element of the array. So yeah, I have utilized one query to find the maximum element of the array, and now what I do is I do this binary search. So while r is greater than l, I find the middle element, and what I do is I create a vector, and in this for loop I take the union of all the slots from L to mid, and this is easy. You just keep on adding all the elements to your vector, and finally you just query for that vector. And again, if that query is equals to max, then you know r is equals to mid, otherwise you know L is equals to mid plus 1. These are just the two cases which we discussed. And finally, when we come out of the binary search, the subset L will actually have the maximum element, if at all there exists at least one subset like that. And irrespective of whether it has the maximum element or not, I'll just query for it separately. So what I do is I take a set and I firstly insert all the elements in it, and then I just remove all the elements in my LH subset, and finally what I'll be left with is the remaining array, and I just push that in a vector, and I query for that vector, and the answer for the LH subset is going to be just the query, and the answer for all the other subsets is just going to be mx as discussed, and finally I just print my answer. So yeah, this essentially solves our problem. So that is it for today. I hope you guys got to learn something new today, and you will be more confident while attempting an interactive problem in a live contest. And yeah, I wish I could help furthermore in the future. Thank you for watching. Bye bye.